Welcome to Math 361, Statistical Methods 1. This is Makeup Lecture 4, covering the end of Chapter 4 on conditional probability. In this video lecture, we will do a quick vocabulary review, followed up by discussion on the general multiplication rule and Bayes' theorem. When we get to slides on group work, you're encouraged to pause this video, go to Blackboard and download the in-class assignments and work them on your own. Afterwards, you can check your solutions against those provided on Blackboard. After you've done all that, then come back to this video and continue on. Furthermore, there's a couple examples in these lecture notes that I will not be working out in detail here. Instead, I will post the worked out solutions to Blackboard and you can take a look at them in PDF form. Permutations versus combinations. This is from last week. Recall that a permutation is when you're dealing with arrangements of objects where order is important, versus the combination where it's a selection of objects where order is not important. So for example, if you had a 5-card poker hand, you'd have to ask yourself, if you switch the order of some of the cards in your hand, would you want to consider that a new 5-card poker hand? If the answer was yes, then you'd be dealing with a permutation problem. If the answer is no, which is the correct answer, you'd be dealing with a combination problem. Statistic versus parameter. This is back from week 1. Recall that a statistic is a measurement taken on a sample, hopefully a simple random sample from a larger population. So something like a sample mean or a sample standard deviation would be examples. A parameter instead is a measurement based on an entire population. So this would be the population mean mu or the population standard deviation sigma. These values, while they always exist, they are always unknown to us. And as usual, our goal is to calculate a statistic and use that to infer something about an unknown population parameter. Mutually exclusive versus independent. Recall that mutually exclusive events are two events that cannot occur on the same run of a random experiment. In other words, if A and B are mutually exclusive, A and B, or the intersection of A and B, is the empty set. The probability of A and B when A and B are mutually exclusive is equal to 0. Independence, however, is based on how we assign probabilities to the events. So the definition of independence, A and B are independent if knowledge of event A occurring does not change the likelihood of event B occurring. Be careful not to confuse the notion of independence and dependence with that of causation. Right? Just because two events would be dependent does not mean that one causes the other. NPR versus NCR. These are notations for permutations and combinations. NPR is when we have n objects, distinct objects, and we want to order them r at a time, versus NCR, which is having n objects and we want to select them r at a time. So if we were counting number of 5-card poker hands, that would be 52C5. If instead we were looking at number of playlists we can make from a library of 100 songs, and we wanted our playlist to be, say, 10 songs long, that would be 100P10. Because there, once I have my 10 songs, if I reorder them, I would consider that a different playlist. So order is important in that situation. Probability A versus the probability of A given B. So recall that the notation on the right, that vertical line is read as given. That is not a set operation. It is just the notation we use for an alternative assignment of probabilities where we have assumed that we have knowledge that B has occurred. All right? So probability of A given B has a very important formula you should have memorized. Probability of A, how we would calculate that, would be dependent upon whether or not all outcomes are equally likely. We could use the classical approach or something else entirely. So at this point, you should go and look at the first page of the in-class group work that was posted to Blackboard and try working on that first page. Leave pages 2 and 3 for later in these lecture slides. So a quick example, are mutually exclusive events independent? Now these questions are good because we want to make sure we don't get confused, and it's easy to get confused between these two concepts. So if A and B are mutually exclusive, that means they cannot occur on the same run of a random experiment. So if A occurs, I know B cannot occur. Therefore, if A occurs, the probability of B occurring should be 0. So when you have mutually exclusive events, they are not independent. They are in fact very dependent. Knowledge that A has occurred tells me that B will not occur because they cannot both occur on the same run. Now, there are some edge cases here where if one of the probabilities is equal to 0, but let's assume that we're dealing with events that have non-zero probabilities. The general multiplication rule is found just by rewriting the definition of conditional probability. Now, to rewrite the definition of conditional probability, we have to assume that probability of A and probability of B are not 0. So let's eliminate those possible edge cases again and look at what this says. It says the probability of A intersect B, or A and B, is equal to either the conditional probability of B given A times the probability of A, or the probability of A given B times the probability of B. I always remember the conditional probability rule by the given event in the conditional probability has to be the same as the straightforward probability at the end. So it's B given A times the probability of A, or A given B times the probability of B. Now, the general multiplication rule, while we could use it to directly manipulate probabilities, is most useful when using tree diagrams to solve conditional probability problems. Now, the reason this is that if you follow the setup for creating a tree diagram for a problem involving conditional probabilities, the general multiplication rule will be built in to the tree diagram itself. So an example here is, suppose you test positive for some rare disease, say tuberculosis, which affects approximately 0.05% of the population. And you're told that the test is about 99% effective. That is, the probability of you testing negative, given that you do not have the disease, is 0.99. This is also referred to as the specificity of the test. You're also told that the false negative rate, the possibility that you test negative given that you have the disease, is 0.001. And we're asked 3 questions here. What is the probability that you have TB given that you tested positive? Right? Just because you test positive, because this test is not 100% effective, does not guarantee that you actually will have TB. As a patient, you care about the likelihood of having TB given that you tested positive. What is the probability that any individual will test positive for TB? And then are testing negative and having TB mutually exclusive? So to see this problem worked out, I would pause the video here and go look at the TB example that is posted on Blackboard, and then come back here. Okay, a second example. This one we could also do with a tree diagram, but instead I'd like to introduce a new way of doing this just with formulas itself. Tree diagrams are great, but when there's multiple conditioning events, they get a little difficult, get a little cumbersome. So at that point, it might be easier just to rely on equations themselves. So this is a pretty classical example here. 3 urns contain colored balls distributed as follows. Urn 1 contains 3 red balls, 4 white balls, and 1 blue ball for 8 total. Urn 2 has 1 red, 2 white, and 3 blue for 6 total. And urn 3 has 4 red, 3 white, and 2 blue for 9 total. Suppose an urn is chosen at random and a ball is withdrawn, and it happens to be red. What is the probability that it came from urn 2? Note that without this knowledge that the ball was red, and we want to know what the probability that the ball came from urn 2 was, we just have to look at the fact that there's 3 urns, 1, 2, and 3, and we're choosing one at random. So without knowledge that the ball is red, the best I could say is that, well, I chose 1 out of 3 urns, so most likely there's a 33% chance that it came from urn 2. But now that we know that the ball is red, how would we like to update that probability? So I would pause the video here and now go look for the colored ball problem write-up on Blackboard, and that will show you a detailed workup of this problem. Now, in the end, the very complicated formula we get out of this solution is known as Bayes' rule. Bayes' rule is stated as follows. The conditional probability of hypothesis H sub k, assuming that there are multiple hypotheses, occurring given evidence E has been observed is given by the following formula. On the left there, you have the probability of H sub k given E. That's the post probability, the updated probability of the hypothesis being true once the evidence has been observed. And on the right-hand side, on the numerator, you have the probability of the evidence given hypothesis K. So that means the likelihood of observing this evidence under the assumption this hypothesis has occurred. On the far right-hand side, you have the prior probability for hypothesis K. So this is the probability of hypothesis K being true before you've collected any evidence. And in the denominator there is the total probability of obtaining the observed evidence. So that's the probability of E. But recall from the previous problem example with the urns and the balls that whole denominator, while it's the probability of the evidence, P of E, we've broken that down through several equations to get down to this final representation here. So there's a sum of quantities, and each one of those quantities is a likelihood of observing the evidence given a hypothesis times the probability of that hypothesis being true. And you have to sum that up over all the possible hypotheses in this problem. And a requirement for those hypotheses is that they're disjoint events, so there's no overlap, and also that they're exhaustive. That means that every possible outcome of the random experiment is contained in at least one of these hypotheses. There's not some outcome that's not associated with one of these hypotheses. Now, you're not expected to memorize this or enjoy this formula at all. And as you saw from the urn example, you don't even really need to know this formula if you can just work through all the connections of the other formulas. But once you get many hypotheses involved, this formula becomes a much quicker way of working these conditional probability problems than the tree diagram we use for the TB problem. We could use this formula here to solve the TB problem without any tree diagram. In that case, the evidence would be whether you tested positive or negative, and the hypotheses would be whether or not you had TB or not. There will be, on the take-home exam, there may be one extra credit question dealing with Bayes' rule, but there will not be a regular problem dealing with Bayes' rule. At this point, you should pause the video and go and attempt pages 2 and 3 of the in-class problems or the in-class group work posted to Blackboard, and then check your work against the solutions. The first problem is a tree diagram problem similar to the TB problem. And the second problem is a Bayes' rule example. Now, we're not going to do any review for exam 1 in this lecture video, and most of this information on this page is no longer correct because, as I stated in the class announcement, exam 1 will now be a take-home exam, so we will not be taking it in class next week. You will still be able to use a graphing calculator and a provided equation sheet, and exam 1 will now be open book and open note, but it is closed internet and closed classmate, meaning you cannot get help from the internet at large, and you cannot get help from any of your classmates in the class. We'll talk more about take-home exam 1 next week, hopefully, assuming it doesn't snow again.